Hello, my name is Victor. I'm from Huawei North Arc Lab. Today I'm going to present our work, Architecture Intact Oracle for Farthest Paths and Time Queries on Dynamic Spatial Networks. I will first give an introduction which includes related works, and then I will formally define the problem. Next, I will present our proposed algorithm and experiment. Finally, I will conclude the paper and propose several future works. So first, what is a root network? A root network consists of vertices and edges, and each edge has a weight. And the physical meaning of a weight could be a distance or travel time. And in this example, there are 8 different vertices, and the shortest path from V1 to V4 is as shown in the red line. And the shortest distance from V1 to V4 is 5. And it is very important to compute the shortest distance and shortest path in real time, especially for some emergency applications, such as delivering ambulances to the target areas. And the root networks are highly dynamic and unpredictable, caused by car accidents, traffic congestions, and public events, etc. Although there are some existing studies on static networks and dynamic networks, they are not efficient enough. Let me classify them into 3 different categories. The first category contains oracles on static networks. So it does not apply to dynamic networks, and it has very large pre-processing time, which is larger than big O n squared. The second category contains oracles on dynamic networks, and it has a very large pre-processing time, which is larger than big O n to the power of 1.5, and it has a very large updating time, which is larger than big O n to the power of 5. And their empirical updating time is not small enough. The third category contains oracles on time-dependent networks, and they assume that traffic is predictable, which is different from our problem setting. So our contributions are threefold. We propose a novel distance and path oracle for dynamic root networks, and we derive theoretical bounds, and remarkably, our oracle is the first one which has a polylog updating time. And we conduct experiments on real and synthetic data sets and verify the efficiency of our algorithms. So this table compares all the oracles on dynamic networks in theory. So the oracles in the red box are adapted from the oracles on static networks. And the oracles in the purple box are the oracles on dynamic networks. So each existing or adapted algorithm has a pre-processing time larger than big O n to the power of 1.5 and an updating time larger than big O n to the power of 1.5. So our oracle has a big O n log square n pre-processing time and a big O log cube n updating time with high probability. So let me define the problem. So let G denote a spatial network, and V denotes the set of vertices, and E denotes the set of edges, and N and M denotes the number of vertices and edges respectively. And WGUV denotes the weight of an edge UV, and DGST denotes the shortest distance from S to T. So in this example, there are 8 vertices, and the shortest path from V1 to V4 is V1, V6, V8, V5, V4, and distance from the V1 to V4 is equal to 5. So our problem is to design an oracle that supports a short update time and at the same time answers any shortest path and distance query efficiently. So let me present our proposed algorithm. So let me first present a very important concept called architecture intact property. So given data structure, the architecture of this data structure is defined to be a set of all components in this data structure, excluding all non-structural information, for example, the weight information. And we say that an oracle constructed from a spatial network satisfies the architecture intact property if the architecture of the data structure used in this oracle remains unchanged even when there is update on the weight of an edge in the spatial network. And each existing architecture has to satisfy many constraints and properties. Thus, it is costly to dynamically maintain an architecture. The reason why our oracle is efficient in terms of updating time is that it satisfies the architecture intact property. So we prove that in our paper that our proposed oracle satisfies the property, but all existing oracles including existing oracles on dynamic networks, and oracles adapted from the ones on static networks do not satisfy. So the second key concept is the rank of vertex. Given an ordering of all vertices, the rank of each vertex V is defined to be the position of this ordering. So in this example, the ordering is V1, V2, V3 until V8. The rank of V1 is 1 and the rank of V2 is 2 and so on and so forth. Thus, V1 has smaller rank than V2. So let me present the next two key concepts. The first one is called valid path. Given an ordering of all vertices, a path is said to be a valid path if the rank value of each vertex along the path except the first vertex and the last vertex is smaller than both the rank value of V1 and VL. So given an ordering of all vertices, we see a path is ternary valid path if it is a valid path and this path involves 3 vertices only. So in this example, the path V7, V3, V4 is a valid path and also a ternary valid path. So in the pre-processing phase of our proposed oracle, update efficient UE in short, first imposes a randomized ordering of vertices, and it promises attractive theoretical performance with high probability. And then it initializes G prime to be the original network G, and then it contracts vertices one by one in order. And in the contraction of vertex O, for each pair of UV, where U and V are neighbors of O, we add a shortcut UV to G prime if UV does not exist in G. So in other words, we add a shortcut UV if and only if there is a valid path from U to V in G. So by doing so, we assure that our UE satisfies the architecture intact property, since the definition of our shortcuts is independent of the weight information and only related to the topology of G and the ordering of vertices. Thus, the topology of G prime keeps intact. And it also satisfies the so-called shortcut property for each pair of vertices, namely U and V, such that there exists a valid path from U to V. G prime must have a shortcut from U to V with weight equal to the length of the shortest valid path from U to V on the original network G. And then it updates the weight of UV to be the minimum of W and W prime. Here, the W is the length of shortest ternary valid path from U to V on the UE spatial network G prime. And W prime is the weight of the edge UV on the original network G. If there is no such edge UV on G, W prime is said to be infinity. And our oracle also satisfies the ternary valid path property. And the shortest valid path from U to V on G has a length equal to a minimum of W and W prime. So in the updating phase, from the edge with a weight update, search and update the effective weights of the shortcuts in a BFS fashion. And consider this example, the weight of the edge UV is updated from omega to omega prime. And consider edge of the in-neighbor of U, whose rank value is larger than that of U. And consider the edge XV. And let W be the length of shortest ternary valid path from the vertex X to the vertex V of the UE spatial network G prime. And let W prime be the weight of the edge XV, if any, on the original graph G. If there is no edge XV on G, and W prime is set to infinity. Then update the weight of XV to be the minimum at W and W prime. If the weight of XV is changed, recursively update the shortcuts affected by the change of weight of XV. And due to property 2, ternary valid path property, it is sufficient to check W and W prime when XV is updated. And it is very efficient due to the architecture intact property. In other words, there's no need to insert or delete shortcuts due to the definition of the shortcut. In the query phase, we first find the shortest path on G prime by performing a bidextrous search with an order constraint. So the order constraint is that we only explore the vertices with higher ranks in the forward and backward search. So in this example, consider the shortest path from V4 to V1 on G prime. So the forward search only visit V7 and V8, and the backward search will visit V6, V8, and the two searches finally meet at V8. And then we further find the shortest path on the original network G based on the shortest path on G prime. And the correctness is ensured due to property 1, the shortcut property. Now let me present the experiment. So in the experiment, we use 8 different data sets with different sizes, and we conduct experiments on a Linux machine with 2.67 Hz CPU and 48 gigabyte memory. And we implement all the algorithms in C++. This figure shows updating time on Great Britain dataset. And as you can see, our algorithm is several orders of magnitudes faster than baselines. Other algorithms are 2 to 3 orders of magnitude slower in terms of updating time, which could not be finished in a reasonable time. Thus, we do not show them here. So this figure shows the query time for all algorithms. Although the query time of UE is not fastest, its query time is fast enough for real applications. In another word, within 1 millisecond. Note that the update time of UE is the fastest, several orders of magnitudes faster than other baselines. So let me conclude the work and propose several future works. In this paper, we propose a distance and a path oracle on dynamic spatial networks. So we derived theoretical bounds on the proposed oracle, and remarkably, it has a polylog updating time. And our experiments demonstrate that our oracle is very efficient and scalable on sizable networks. And it is interesting to further design more advanced updating algorithm for UE. Thank you very much for your listening.